Hello and welcome to Math 452, Mathematical Statistics. So this is the first lecture for spring 2021. And before we jump into the lecture material, I just want to go through the resources for the course. So of course we have our Blackboard page, where primarily you'll be submitting homework assignments. We'll do exams through Blackboard, and I'll send announcements through Blackboard. Additionally, we have this GitHub page here, gjhunt.github.io/452 spring 2021. And this is going to have some more kind of day-to-day information. And we'll have a link on Blackboard to this website, but I'll post the lectures, notes, and I'll post homeworks and readings and things like that. So I'll send out an announcement, and you'll get that before you actually get this lecture. And explaining some of that material. We have a course outline, which is kind of a very rough course outline. Important dates being the midterm, so midterm 1, midterm 2. And we have a welcome announcement, which I'll send out on Blackboard, talking about all aspects of the course, lectures, the books, office hours, and how you're going to be graded for the course. So let's not dawdle anymore. And let's jump into our lecture material. And kind of fittingly, the first lecture for mathematical statistics is titled just Statistics. So we're first going to do some review of random samples and statistics. Some of this you may have seen, some of this you may have seen and forgotten. But we're going to kind of do a review here of what's going on. So let's say random samples and statistics. Okay. So the course is called Mathematical Statistics, and obviously we're going to study statistics, so we need to talk about what statistics are. The course is going to basically talk about how do we estimate quantities of interest, and what properties can we, state or figure out about estimators? What makes a good estimator? What makes a bad estimator? And how can we kind of efficiently or robustly estimate quantities? So the first thing we want to talk about is we're going to give just a definition of what a random sample is. So for the sake of this course, we're going to say that a random sample is just going to be a collection of mutually independent random variables. So if I have some random variables, x1 to x capital N, so here my notation is that this Blackboard bold x is a random variable, and n here is basically what we're going to call my sample size. But if we have these x1 to xn, and they are mutually independent, or we could just say independent random variables, RVS, and they all with marginal, it's supposed to be AL, marginal distribution. And we're going to generically denote the marginal distribution of all these as some F. So this is basically the marginal. When I say marginal distribution, I mean kind of the marginal PMF or PDF. So x1 to xn are mutually independent random variables, and they all have some same marginal distribution. Generically, we're just going to note it as F. So if this is the case, then we say that x1 to xn are a random sample from F. whatever f is. And one way you could denote this is to say that x sub I are distributed, independent and identically distributed following f. So that's the notation. X sub I are IIDF. And maybe we shouldn't use I. Let's use n here. Let's say x sub little n. So little n is just my index, 1, 2, 3, up to capital N, which is my kind of total sample size. And here, again, my notation, this is read as independent and identically distributed. X or IIDF. So this is our definition of a random sample. Random sample is just a collection of some number. Typically in this course, we're going to use capital N, some number, capital N, random variables. They all have some same marginal distribution, and they're independent of each other. They're independent or a random sample of f. And typically we kind of suppress the fact that they're independent. So there's some notation here that we should just kind of clear up. The notation here I'm using my Blackboard bold x's with the kind of double cross here, x1 to x sub n. These are my random variables. I could put them some parens around them, make them a vector. This would be kind of a random vector or a multivariate random variable. And if I wanted to denote the collection of these, maybe I would write this. I would say x, and I'll put a tilde under it. So x tilde is going to be the vector or the multivariate random variable x1 to x capital N. The elements are random sample. The elements are independent. They all have some marginal distribution f. So this thing, right, this is a multivariate random variable or random vector, however you want to think about it. I'm going to use the notation little x, so it's maybe curlier, and I'll put a tilde under that to denote it's a vector. And that's kind of my way of denoting vectors. And that is just going to be kind of a classic vector. It's just an n-dimensional real vector. Okay, so tilde means it's a vector. Typically, I guess this should be capital N elements. And if I make it bold by putting the extra hash through it, the extra cross through it, that's a random variable. So this thing is just a real vector. So the first thing we should note about a random sample is that if I want to look at the joint PDF of my random sample, so I'm going to note that with a capital F. So I'm going to be a bit lazy here, or a lowercase f, but I'm going to be a bit lazy here. I'm not always going to differentiate the joint from the marginal. So this here is going to be my joint distribution. And the joint distribution, of course, is evaluated at some number. So we may have seen this previously, it's f of x1 to xn, right? I'm just going to be lazy and write f of x tilde because I don't want to write x1, x2, etc. Again, capital N. This is my joint distribution. This is the same joint distribution in different notation. And the joint distribution is, in our case, is just going to be the product of the marginals. It's f of x1 times f of x2 all the way times f of xn. And why is it the product of the marginals? It's the product of the marginals by independence. So here, again, I'm being a little bit abusive with notation. This f here is the marginal. We said all of the x sub i's have some marginal distribution, little f, so that's that marginal distribution. I'm going to use the same f for the joint because, frankly, the relationship is pretty easy. The joint distribution is just the product of the marginals evaluated at each of the x sub i's. And this is by independence, and this is basically more or less a definition of independence, or functionally what people use as the definition of independence, which is that you can factor joint into the product of the marginals. We can write this in notation that I'll use in this course is again, I don't want to write f of x1, f of x2. I'm going to say it's capital pi, and let's say little n goes 1 to big N of f of x sub little n. So this is kind of similar notation to sigma notation. So let's say similar notation to, we write sigma of x sub I, right? I goes 1 to n if we mean x1 plus x2 plus dot dot dot, right? Here, because instead of having a sum, we have a product, I'm writing pi, n goes 1 to n of the fx. This is a notation that you'll see. It's just a product of these things. So first thing to note is that if I have a random sample is basically just a collection of independent, identically distributed random variables. It has some marginal distribution, little f. If I have a random sample, the joint distribution is just a product of the marginals, and all the marginals are the same, right? So we should note here that all the marginals are the same, and by independence we can factor it out. Okay. Let's look at some examples, some concrete examples here. So, let's go with green here. Example. If I have a random sample, let's say some x sub n's, and they are IID from an exponential distribution with some parameter, rate parameter, lambda, let's say. That's certainly possible. So to refresh your memories, if, let's say, some random variable y has an exponential lambda distribution, then the marginal PDF, so exponential is a continuous random variable, the marginal PDF is lambda e to the negative lambda y, and this is for y bigger than 0. One way we can write this as one line, so some notation we're going to introduce here, is we can write it as lambda e to the negative lambda y, and then I'm going to do something a little bit funny looking. I'm going to say 1, a bold 1, of y bigger than, y bigger than 0. So this thing is called an indicator function. And an indicator function, which I'm going to denote by 1 of some statement is 0 if statement is false, and 1 if statement true. So basically some shorthand notation. So it's 0 or 1. Indicator functions at the beginning, you're going to think they're very annoying, but they're going to help a lot with mathematical statistics. It's just something fundamentally the statisticians have to learn how to manipulate. So indicator functions are just basically, I say, one of some statement, and that is going to produce a 0, the same as false, and a 1, the same as true. So when I include it here in my definition, this is kind of a more adult way of writing the PDF. So typically in, say, a 451 class, we'd first write that the PDF of an exponential distribution is lambda e to the negative lambda y for y bigger than 0. You could instead write it is lambda e to the negative lambda y, indicator y bigger than 0. And that will give you the correct thing, right? Why? Because if y is bigger than 0, this indicator function basically goes away. It just becomes the number 1. You're just multiplying by the number 1. So it's lambda e to the negative lambda y if y is bigger than 0. If y is less than 0, the indicator function here becomes 0. And so you multiply whatever by 0, and the whole thing goes to 0. And that we know is the correct way of specifying the PDF. So typically, you'll often see this happen where whenever you could write something like for y bigger than 0, or for whatever the support is of the random variable, you could instead say indicator of the support. So let me just write that down. So we'll often see f of y equals something times indicator of y in the support. And that's always a valid way of writing it because that's kind of definitionally how the support is defined. And that will give us basically the case where our PDF is whatever if y is in the support and 0 if y is not in the support everywhere else. So that's kind of the more kind of adult way of writing out PDFs. And it allows you to write it out on one line. You don't have to have a for statement in there. It's a valid function. It's called an indicator function. And we're going to be able to manipulate them like we can any other kind of algebraic expression. So not in this lecture, but they will come up quite a bit in this course. And so they're going to be something that we're going to learn how to manipulate. Okay. That was an aside. Back to our main point here. Our example was we have a random sampler from the exponential lambda distribution. And so what's the joint PDF? What's the joint? So we know that f of x tilde is the product of the marginal distributions, the x sub n's. And each of these x sub n's has a marginal distribution. That is, or maybe we should say it's the second line here, which is this one. It is the product lambda e to the negative lambda, and now instead of y, it's x sub n. So it's the product of those things. And I guess we forgot our indicator function, right? Indicator that x sub n is bigger than 0. Don't forget that. Indicator functions are just functions like any other kind of algebraic function. We can manipulate them. So we could simplify this a little bit. You know, you could pull out a lambda to the n. Lambda to the capital N. So here again, capital N is going to be typically my sample size unless otherwise specified. And we will get an e to the negative lambda times the sum of these x sub n's. And then we're going to get a product of a bunch of, so I'm going to say multiplied by product of that x1 is bigger than 0, indicator that x2 is bigger than 0, ... all the way xn bigger than 0, right? So we're going to get a product of these indicator functions that's left over. And that's for now, that's just how we're going to leave it. Yeah, and so that's a nice little refresher on what's going on here. But so there's a sample. We have data, some random sample. Maybe it comes from, we assume it comes from an exponential distribution with some parameter lambda. That would be the joint distribution of the data. Okay, so the title of the course, the title of the lecture is Statistics. So let's define what a statistic is, right? And you might think it's some grandiose definition. Turns out, not so. Statistics are a very general concept. So definition, statistic. A statistic is basically a function. Let's say given a random sample. I'm probably going to suppress writing that from now on, but we'll say given xn, which are iid from some distribution. That is, they are a random sample. A statistic is a function t, and t is going to take in real numbers in Rn and spit out real numbers in some other space, Rd. So here again, n is my sample size. And typically, so we're done with our definition. Given the random sample, xn, iid, f, a statistic is a function from Rn to Rd. Typically, d is, let's say, much less than n. Often, d is equal to 1. Doesn't have to be. The idea being with a statistic is that, why do I say typically d is much less than n? A statistic is going to take data, it's going to take a random sample, which is data, and it's going to summarize it. Functions summarize things. So it's going to take in n numbers. You're going to input some n numbers, and my function t is going to spit out a summary in lower dimension. Let's look at some concrete examples here. The most obvious statistic is the arithmetic mean. Right? So t of x tilde is t of my sample is 1 over the sample size, the sum of the values of my sample. In this course, we will denote the arithmetic mean. We're not going to call it t of x. We're going to call it xn bar. That's the arithmetic mean, right? So, but this thing is a function. It takes in n numbers, or an n-dimensional random vector, and it spits out one number. So here, d is equal to 1. I've summarized n numbers down to a single number using the arithmetic mean. That's obviously our favorite example. But there are other examples. Let's say sample variance. These are things you might have seen, say, in an introductory statistics course. In this course, we're going to denote this as s squared with a subscript n minus 1. And that has the formula 1 over n minus 1. the sum of my x sub n's minus my arithmetic mean. You square those and you sum them up. This is called the sample variance with an n minus 1 denominator. And this thing is a function, so is it a statistic? Yes, it's a statistic. It's a function of my x sub n's. Right? There's a formula there. You calculate the arithmetic mean, that's a function, then you take these differences, you square them, you sum them up. That's a statistic. And it's summarizing all that data down into a single number. The mean is going to tell me about the location of my data. The variance, sample variance, will tell me something about the spread of my data. You could also define, say, the sample standard deviation, which we could call S n minus 1 is the square root of my sample variance. There are lots of statistics that you can come up with, but they're all just functions of my data, of my random sample. You can come up with, say, minimum. It's supposed to read minimum. Say x1, maximum, xn, what else? Range, which is the difference, the maximum minus the minimum, and so forth and so forth. These are all functions of my data. Why is the minimum a function of my data? What I do is I take my data, I order it, and I pick the minimum, right? It's a function of the data. So back in 451, we spent forever talking about transformations of random variables, functions of multivariate random variables. Why? The reason, it's not just to torture students, the reason is because you're basically talking about statistics at that point. Statistics are just functions of random variables. And so if you want to talk about, okay, if I have data, what if my data has an exponential distribution? And I want to talk about, well, what if I calculate an arithmetic mean? Is that a reasonable thing to do for my data? What are the properties of the arithmetic mean if my data is exponential? Well, what I need to do is know something about transformations of random variables. And that's why a lot of 451 is kind of building up to this course, building up to transformations. So kind of underwhelming definition of statistics, which is basically just any function of random sample is basically considered a statistic. Another definition that you'll see is a sampling distribution. And you often see this may be in an introductory statistics course. It doesn't really come up as much in kind of adult statistics, as it were. We can give a formal definition to a sampling distribution. So a sampling distribution of a statistic is the distribution of let's say the sampling distribution of a statistic, let's call it a statistic T, is the distribution of T of X. So it's kind of a, again, maybe a underwhelming definition. When people talk about sampling distribution in statistics, what they're really thinking of is if my data has some distribution and my statistic is a transformation of my data, is a function of my data, what's the distribution of that function of my data? Probably the only time in this course we're going to use the word sampling distribution, but it's a useful connection back to, say, an introductory statistics course. Talk about, ooh, it's the sampling distribution of X bar. What you're talking about is what is the, if I make some assumption about what my distribution of my data is, what is the resulting distribution of X bar or something? And we will have a lot to say the distribution of x bar. So let's get into that. Maybe we can write down a little theorem. Here's the theorem. First theorem in the course. If I have a random sample and they come from a normal distribution, this normal distribution has a mean mu and variance sigma squared, then introductory statistics tells us that, introductory statistics tells us that the sampling distribution, oh, there it is, sampling distribution of x bar is also normal with a mean mu and a variance that is now sigma squared divided by my sample size, capital N. Underline it. That's the theorem. So we're going to talk about x bar here a little bit. A, because it's probably the most important statistic. And B, it gives us a nice way of talking about some statistics and talking about some properties. So you can think about how to prove that. But we're going to kind of hold off on that here. This is an example of a sampling distribution. So you might have seen this in a 451 course. You might have seen something that looks a lot like this in the introductory statistics course. If I have data that's normal, then my mean of that data is also normal. The mean stays, the arithmetic mean, the statistic x bar is normal. The mean stays the same at mu, and the variance decreases by a factor of n. We might prove this one today. We'll prove it very shortly if we don't. But that's the sampling distribution. This thing would be what we'd call a sampling distribution. If it's not obvious to you why that's true, that's okay. We will show it. But before we get quite there, let's make some more general statements about x bar, because it is this very kind of important statistic. And we want to talk about first about kind of sums of random variables. X bar, the arithmetic mean, is basically it's basically a sum that's been renormalized. We divide through by n, but it's basically a sum. And sums of random variables are kind of simple enough that often we can actually analyze what's going on, and very important to the study of statistics. So this theorem is about sums of random variables. Let's first let g be just some function, some real valued function. And we're going to have a random sample, some xn's from some distribution. We don't even know what the distribution is. It's some distribution f. The theorem is that if I look at the expected value, the theorem will have two parts, but the first part is that if I look at the expected value of the sum, plugging each of my xn's into g, this is n times the expected value of g of x1. Okay. Let's put a box around that. That is the theorem, basically. The first part of the theorem. So a couple things to note. So first of all, basically what I'm doing is we're going to take our random variables and we're going to throw them on some function. Doesn't really matter what function it is. This will work for any function or no function at all. If I take those as transformed things and I sum them up, the expected value of the sum of them is just n times the expected value of any of them. So of them. So let's say expectation of any of them. So could use x1 here is not particularly important. Could use x2 2 or x3, etc. They all have the same expectation, right? So if they're independent and identically distributed, the expected value of x1 is the same thing as the expected value of x2, right? And so this expected value g of x1 surely is the expected value, same as the expected value of g of x2, etc. All right, so the 1 here is not particularly important. It's just they all have the same expected value of g of whatever. Expected value of g of x1 and x2 and x3, etc. are all the same. The important point of the theorem is that the expected value of the sum of all of them is n times the expected value of any of them individually. This is not too hard to prove. This should be provable with kind of 451 level knowledge. What we need to do is recall that expectation is linear. So the expected value of a plus b is the expected value of a plus the expected value of b. And if we do that, we can do this maybe in one line. Expected value of the sum is, well, this is using this kind of repeatedly using this linearity property, I can pull that sum out. And this is sum of the expectations, but of course they all are the same, right? As we said here, expected value g of x1 is the same thing as g of x2, is the same thing as g of x3, etc. And so this is just n sum of something n times, whatever that thing is. So it's n times the expected value of g of x1. Again, x1 or x2 or x3 doesn't matter. Pick your favorite one. They all have the same expected value of g of them. Important point is that if I sum them up, the expected value of the sum of them is n times the expected value of any of them. And that's a proof. We can come up with a kind of similar theorem for variances, which is that the variance of the sum of a function of these things is n times the variance of any of them. So this is the variance version. Proof. Very similar to above, but in order to get the linearity property, here we've said that the expected value of the sum is the sum of the expected value. Generally, that's not true for variances. We have to use the fact that, what am I writing? Similar to above, using fact that the variance of a plus b is the variance of a plus the variance of b if a and b are independent. So we need the independence, but we have it. We have a random sample, right? And we said they're independent and identically distributed. They're all independent, so we can play this game, breaking the variance up of the sum. So we're good. And basically, it's going to look very similar about proof. This also will work if they're uncorrelated. Independence is actually a more strict condition than we need. If they're uncorrelated, we can play the same game of splitting up the variance of a sum. So independence is more than we need. Nonetheless, is true. They're independent, they're uncorrelated, theorem holds. But you could similarly say if I have a bunch of random variables that are uncorrelated, this similar theorem would work. Okay. So let's talk about x bar. The reason we wanted to talk about sums here is because it allows us to talk about x bar. right? So now we can say some interesting things about x bar. Eventually what we want to do is get back to this theorem about if xi are normal, then then x bar is also normal with some properties. But we can prove kind of a related theorem. So here's the theorem. It's supposed to read theorem. Let's try this again. Okay. Again, we're going to have some random sample. And we're not going to assume we know much about the marginal distribution of these random variables, except that we know that the expected value of all of them, any of them, is some constant mu. And we know something about the variance of any of them. The variance of any of them is sigma squared. Right? They all have the same variance and the same mean because they're identically distributed. And we're going to say the mean is mu and the variance is sigma squared. If we know this, what can we say? We can say that the expected value of the arithmetic mean is going to be mu. So the mean of x bar is mu, right? So let's back up here. X bar is a function of these x n's. X bar is random, right? It's just a function of random variables. Functions of random variables is random. Is a random variable. And so it has an expectation, it has a variance, has all these other properties, has a distribution. And one of the properties is that if I have a random sample and they have some mean mu and variance sigma squared, then the expected value of the arithmetic mean of those random variables is just the same mean, mu. Furthermore, the variance of the arithmetic mean of a collection of random variables is not quite sigma squared, it's sigma squared reduced by n. And the expected value of my sample variance is going to be sigma squared. So let's just take a second to comment on these. The first one basically says that the average value of x bar is mu. Okay, so one way to think about this is that if I have a random sample, I draw a random sample and of n, of capital N things, and I take the arithmetic mean of those. And I do that a bunch of times. I build up this kind of sampling distribution. And on average, the mean of that sampling distribution is going to be the same as the mean of any of the samples I've individually. So if I want to estimate, if I have some data, we're not quite to estimators yet, but if I have some data, we'll get there. If I have some data, some random sample, and I don't know what its mean is, what do? I calculate the arithmetic mean. Why is that reasonable to do? One of the reasons this can be reasonable to do is because on average, the arithmetic mean will give us the correct answer. It's going to give us mu. The second property of the arithmetic mean is that the variance of that estimate is not always going to give us exactly, if I draw a sample, it's not always going to give us exactly the mean back mu. Sometimes it'll be too high, sometimes it'll be too low. On average, though, it will get it right. And the variance of the estimate will decrease as the sample size increases. As n, my sample size increases, the variance will go down like 1 over n. This is saying that more data is better. We all have this kind of intuition that, yeah, I want to figure something out, the more data is better. Why? Why is more data better? Well, here's a reason why more data is better. Because, for example, I want to estimate the mean with the arithmetic mean. I'm going to get a tighter sampling distribution, more collapsed around the mean, if I have more data. So points 1 and 2 here, you can kind of summarize in a little image. If I have a low n, I'm going to have a kind of big variance. So if this is my sampling distribution. And so I have a sampling distribution. Its mean is mu, but if I take a sample and calculate arithmetic mean, it's not always going to land exactly at mu. Sometimes it's going to land a bit above it, sometimes a bit below it. If I have a low n, I'm going to have a kind of very wide distribution around mu. Sometimes it'll be quite far from the true mean. Sometimes it'll be quite far above. If I have a higher n, and I look at my sampling distribution, again, the first fact says that it's still always going to be centered around the mean. But it might have a much, that's not well drawn, it might have a much tighter distribution around the mean. So this variance here, which kind of tells me how wide my distribution is, it's going to be, the variance is much smaller because it decreases like 1/n. And so I'm going to have the distribution is going to be much more concentrated around the truth. And I'm going to be more likely to be closer to the mean here, to the true mean. So we're kind of getting to this topic of estimation, which we haven't quite gotten to in the course. We'll get to it maybe not next lecture, but 2 lectures from now. But you can't avoid talking about it, right? So properties of x bar, of the arithmetic mean, is that on average, it's going to tell me what the truth is from my underlying data. The true mean is from my underlying data, or the mean of my underlying data. And more data is going to be better. It's going to be a tighter distribution. The sampling distribution of x bar is going to be more tightly packed around x bar, the more data I have. This third fact is not actually about x bar. It's about the sample variance, S squared. And it also basically says that on average correctly estimates sigma squared, the variance, right? If I gave you a collection of, a random sample, and I said, I don't know what the variance of this thing is, what would you do? You'd calculate the sample variance. Why is that reasonable to do? Well, on average, just like with the mean, on average, the sample variance would be correct. You notice I don't say the variance of the sample variance, which is a confusing sentence. It's a more complicated picture. Let's sketch some quick proofs of why this is true. And the proofs are not maybe too insightful, so we're not going to dollop too much here. But it's good to kind of see how the sausage is made once in a while. So the first fact we want to prove is that we want to prove that if I have a random sample and I calculate the arithmetic mean, right? Data is random, function of the data is going to be random. So we have a random samples, this is a collection of random variables. Any function of those random variables is a random variable. X bar is a function of those random variables. It has an expectation. Turns out its expectation is the mean, mu, of the underlying data, the underlying random sample. How we're going to prove this? This is basically our previous theorem, right? So the expected value of arithmetic mean is, of course, just 1/n, 1/n times the sum of the x sub n's. I can pull constants out of my expectation. So I can just say, in fact, I can pull constants and I can pull the sum out of my expectation, right? And so we have 1/n times the sum, or 1/n times the sum of the expected values, and each of those things has an expected value of mu. And so we get 1/n times n mu's, which of course just gives me mu. So the first fact is actually not so bad. Second fact, a little more work. The second fact is that the variance of my arithmetic mean is sigma squared over n. This is a similar kind of game, right? So let's just write out what the arithmetic mean is. It's 1 over n times the sum of the x of n's. I can pull constants out of variances, but I must square it. And our previous theorem by previous theorem, I mean, if we go back up to this one that talked about sums of random variables, why did we prove this one? The sum of the variance of the sum of things is just n times the variance of any of them, assuming they're independent or at least uncorrelated. And so this 1 over n squared times n times, this just, we could say, is the variance of x1. In this case, g is just the identity function. And the variance of x1 is, so obviously this simplifies to 1 over n. The variance of x1 is just sigma squared. Voila, you get sigma squared over n. So that's our second fact. So our first fact is the expected value is mu of x bar is mu. The variance of x bar is sigma squared over n. Notice this is for any random variables with the mean and the mu and the variance sigma squared. And the last fact is kind of a similar fact about the sample variance. So my third fact, and this one just a bit of algebra. The third fact is that I want to show that if I take my sample variance, this thing should be sigma squared. That on average, the sample variance is kind of correct. This is basically just some algebra. So I'm gonna write a fact here. The fact here is that if I look at basically, I ignore the constant out front. So let's just look at the sum of xn minus x bar squared, right? If I divide this by n minus 1, that would be the sample variance. Turns out you can show, and this is purely algebra, so you should be able to show this, that this is just the sum of the xn squareds minus n times xn bar squared. So let me say here as an aside, why should that look familiar is that this looks kinda, it's very related to, kinda like if I looked at the variance of a random variable y, it would be the expected value of y squared minus square of the expected value. Okay, that's a fact from 451. This has a similar-ish form, where this is basically like the variance, and this is like the squared, the expected value squared, and that's kind of like the square of the expected value. Not quite, but pretty much. So there's my fact, which is that if I take that numerator, I can actually break it up as the sum of the squares minus n times the mean squared. Purely an algebraic proof to show that. So nothing too difficult, just manipulating some symbols. But if I do that, what I can do is I can rewrite this thing as, and hell, let's bring the 1 over n minus 1 outside. So I'll bring that 1 over n minus 1 minus 1 outside. I'll be left over with, instead of this numerator here, I can rewrite it as this. So it's right. I'm allowed to rewrite that if you believe my fact. And then I'm allowed to distribute. So let's still have my 1 over n minus 1 outside. I can do a couple moves. First of all, I can distribute this expectation over the subtraction. So the expected value of the sum of the xn squareds minus, I'll close that, minus, now I have an n I can pull out, and I have that n minus 1. Okay, so that's what I'm just distributing the expectation across this minus sign. And I can actually distribute this expectation over this sum here. So let's do that too. 1 over n minus 1 sum of the expected value of xn squared minus n over n minus 1. Okay. So as I claimed, we're just doing some algebra right now. We're just rearranging things here. The second fact I want to bring in here. Ooh, look at this. I can rearrange this formula, and I could say that the expected for any random variable y, the expected value of y squared is going to be the variance of y plus the expected value of it squared. Right? I'm just rearranging my variance shortcut formula. And so if I recall that the expected value of my xn's is mu, and the variance of my xn's is sigma squared, and the first two facts we showed is that the expected value of xn bar is also mu, and the variance xn bar is sigma squared over n. I can basically use this fact here and figure out what all these expectations are. So the expectation, so we have an n minus 1, we have a sum, we have the expectation of any of my xn squared should be sigma squared plus mu squared, right? Sigma squared plus mu squared. Variance plus expectation squared. And then I have minus n minus 1 over n. And I also get variance, in this case the variance of xn bar is sigma squared over n. And the expectation of xn bar, which I need to square, should be a mu squared. And I guess I can I don't even have to write that as a sum. They're all the same, so it's just n of those. If I do some algebra, you should sit and do the algebra and convince yourself that gets me sigma squared. So cool. So that's the theorem. That is the theorem. So the theorem, that third part of the theorem was showing that, of course, that expected value of the variance squared is, expected value of the variance is sigma squared. So what we saw is that in this theorem, if we go back up to our theorem, the three parts of the theorem were that, let me just put a line here. First one, the expected value of x bar is mu. The second is the variance of x bar is sigma squared over n. And the third was the expectation of the sample variance is sigma squared. So these first two, let's rewrite the first two facts. What we saw is that if we looked at a statistic, say xn bar, that gave us mu. And if we looked at the expected value of a different statistic, namely the sample variance, Sn minus 1 squared, that gave us sigma squared. This leads to a definition that you'll hear in statistics. And the definition is unbiased. So we say a statistic is unbiased for a quantity And let's just generally call that quantity theta. Doesn't matter what it is. For quantity theta, if, let's say, a statistic, let's give it a name, a statistic t is unbiased for some quantity theta, if the expected value of my statistic, t of x, is theta. So unbiased is really just a rebranding of saying the expected value. If you say t is unbiased for theta, all it's saying is the expected value of t is theta. So in our example, what we saw is that x bar is unbiased, or an unbiased estimator for the mean of the sample, and the sample variance is unbiased for the true variance. And so this is why these are common estimators. You want the mean of something, of some set of data. Our theorem says we didn't make any assumption about any underlying distribution, any fancy property. If it's just, we had a random sample, if I want to get an estimator for the mean, I could use the sample, the arithmetic mean. If I want to estimate the variance of my sample, I don't know what sigma squared is. I could calculate the sample variance. Why are these good estimators? Well, one nice property. There are other properties. We will basically spend the whole course talking about properties of estimators. Is that they're unbiased for the quantities that they estimate. On average, x bar is going to tell us what the underlying mean is. On average, the sample variance will tell us what sigma squared is. And so if you ever wondered why in my formula for the sample variance, we go back up from my formula for the sample variance, way back up here. Why is there an n-1 in the denominator of my sample variance? The reason is because it gives me an unbiased estimator. Is that on the expected value, with n-1 in the denominator, the expected value is sigma squared. If n-1 weren't in the denominator, you can work out what it would be. If I use 1 over n, you get something that's slightly wrong. Or on average is slightly wrong. Now, that's not necessarily the worst thing in the world. There are reasons you might use something that is a biased estimator. Sometimes they work better, and we will definitely talk about that in this course. But a property, and a reasonably nice property of an estimator, is if it's unbiased. So the reason why even n-1 the sample variance is because it gives us an unbiased estimator of the true underlying variance of our data. The deeper question, of course, is why n-1? Why is n-1 the denominator? Why does the n-1 give us an unbiased estimator? That's a much deeper question that involves some linear algebra. And we might hit on it a little bit next time. I can maybe hint at it. Has to do with the rank of certain matrix, but the dimension of a certain subspace. But for now, you can hopefully be satisfied that the reason why you have n-1 denominator of sample variance is because it's an unbiased estimator. Not really that big a deal if your sample size is big, because it doesn't change. 1 over n or 1 over n-1 is not really that much different. So that's kind of some simple statistics about x bar. What we want to start talking about now is the next thing we're going to get into is talking about what other properties can I know about, let's say, x bar, if I know something about my data. So the theorem that we had kind of worked up to in this lecture, we don't actually know much about our data. All we know is it's a random sample. We don't know it has maybe the data has a gamma distribution. Maybe the x's have a Poisson distribution. We actually don't know anything. And the most natural place to start is we're going to start with talking about data that has a normal distribution. So if we have normal data. And so that's kind of where we're going to start working towards. So the theorem, heading that direction, is going to be about moment generating functions. MGFs of random samples. And I'm going to use RS for random sample. Thought you could avoid MGFs, but they're back. They're very useful. They're not just there to torture you. MGFs are super useful. So again, most of our theorems are going to start this way. We have a random sample. So we have some data. It's independent, identically distributed from some distribution F. If this is true, we could ask, for example, what is, maybe I should rename my theorem, MGF of X bar. What is the MGF of X bar? Okay, right. The data, the X of n's are random. X bar is a function of the data, therefore X bar is random. So you got to get used to in this class is that as thinking of statistics not as numbers that you calculate, but as random variables. Because ultimately they are. They're a function of random variables, and therefore they are a random variable. And so X bar is a random variable. It has a mean, has a variance like we saw. It also has a moment generating function. And the theorem is that the moment generating function of X bar we can write as M moment generating function of, let's say, of any of them, M x of n, evaluated at t over n all to the nth power. So again, here capital N is my sample size. So, so let's put a box around that. That's the important fact. And the theorem basically says that if I know the moment generating function of my underlying data, the moment generating function of X bar is just the moment generating function of my underlying data evaluated at not t, but t over n, and I raise it to the nth power. And this, again, is, I think, a kind of 451 accessible proof. So proof, or let's think about why this is true, whatever you want to call it. I'm a statistician. I am not a mathematician. M x bar of t, the moment generating function of x bar, right? So what's a moment generating function? It is the expected value of e to the t, whatever the random variable is. In this case, our random variable is x bar. So expected value of e to the t, x bar. Let's expand this out a little bit more. X bar is 1 over the sample size times the sum of our data. And I can now use some nice, let's say, tricks of exponential functions, some algebra here. I can pull that sum out, and I can use a property of exponentials and say that this is the product of e to the t 1 over n xn. Right? So that's just using a property of exponential functions, which is that e to the a plus b is e to the a times e to the b. Right? And so if I have e to a sum, I can write it as a product of exponentials. You can sit and think about why that's true. That is true. Some algebra. And the next trick I'm going to pull here is actually a probability trick, which is that I claim I can pull this product sign, this product operator, out of the expectation. And that I can write this as the product of the expected value of e to the t and x bar. Why? This, reaching back to 451 knowledge, is by independence. So this is true. It's true by independence. I can break up the expected value of AB as the expected value of A times the expected value of B if and only if, well, they're uncorrelated. But certainly if they're independent, I can break them up in this way. So if they're independent, which they are, they're a random sample, I can push expected value through. And now we just need to recognize at this point that this thing, e to the t over n xn, is the moment generating function of x sub n at t over n. If you're to write down, if I said, what's the moment generating function of xn at t over n, that's what you'd write down. Write that down. And in my theorem, really, we shouldn't write x sub n here. We really should write more concretely x sub 1. Reason being is that all of these moment generating functions are the same. And so I could say that this is m of x1 is the same as n of x2, is the same as n of x3, etc. Right? The random variables are all the same. They're identically distributed. Their moment generating function is all the same. So I could write this as m x1 t over n times m x1 of t over n dot 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 dot. And I could do that a total of capital N times. And so what I get is m. And what I get is exactly what I claimed in the theorem. So again, mostly just some algebra, one little trick about independence, and you got to recognize that all these moment generating functions are the same. And again, I could pick, it doesn't have to be x sub 1, it could be x sub 2, it could be x sub 3. It doesn't particularly matter here. They're all the same. So pick your favorite number. So that's a little useful theorem. The main reason we want this theorem is because what we want to do is we want to ask the question, if I know something more about my data. So previously we saw that if my data was just any random sample, we had these kind of 3 facts about, or at least 2 facts about x bar. Well, what if I know my data is normal? In fact, I claim that if my data has, way back up here, I claim if my data is normal, x bar is normal, with a mean mu, well, we've seen that before, and a variance sigma squared over n. We've seen that before. So we can actually prove this theorem now. And the theorem is that if I have a random sample, scroll way back down here, and it's not just that they're identically distributed, but they're all normal with the mean mu and variance sigma squared over n. I'm sorry, and variance sigma squared. Then, as we claimed above, kind of at the beginning of this lecture, x bar is also normally distributed. Mean mu, variance, not sigma squared, but sigma squared over n. So you could write this as a theorem. Sure, it's a fact. And we can prove it. We can prove it, not surprisingly, using this previous theorem we just looked at. And here you start to see why MGFs are so powerful. MGFs are incredibly powerful for talking about sums of random variables, which the mean is basically a sum, and then you divide by n. So the proof is that mx bar is, of course, we said it's the moment generating function of any of them divided by n to the nth power. Okay, what's the moment generating function of any of my x, of x1 or any of my x's? Well, you have to remember that if I have data that follows a normal distribution with mean mu and variance sigma squared, then the moment generating function of this, and this is a fact I don't have memorized, you shouldn't memorize, but it's a fact you could look up, is mu t plus sigma squared t squared over 2. Okay. Sorry. Exponential of mu t plus sigma squared t squared over 2. And so if I plug this in here, so that's the MGF of normal. We derived that in 451. Plug that in here. What do I get? I get exponential of, now instead of t, I'm plugging in t over n. So it's mu t over n plus sigma squared t squared over 2n squared. Close my friends. All of that to the nth power. Now, again, using some facts of algebra, I can push this n through, right? Algebra says that e to the a to the b is e to the ab. That's kind of an algebra fact. And if I do that in this case, I get exponential. I can push my n in. That's just mu t plus sigma squared. Let's write it like this: sigma squared over n t squared. And the kind of completion of the proof is that notice that that is the MGF of a normal distribution with mean mu and variance sigma squared over n. What do I mean by that? I mean, if I said, okay, I have a random variable with that's normally distributed with the mean mu and variance sigma squared over n, what would its MGF be? Its MGF would be this. So the MGF of x bar is the MGF of a normal mu sigma squared over n. So x bar, because MGF basically tells everything about the distribution, x bar has to have. So x bar has to be this distribution. And that's what I claim in the theorem. So that's probably a good stopping point. Let's just do a real quick overview of what we've done today. So we're talking about statistics. Talk about a random sample. That's just IID from some marginal. And talk about indicator functions. Just do a little bit of review on that. Make sure you'll see them a lot, so you'll get enough practice. Statistic is just a function of random variables because the random variables are random. The function of random variables is also random. Statistics are random. So you got to think of statistics as random variables. Sampling distribution is just the distribution of a statistic. And we talked about, we had some theorems about nothing too bad, kind of 451 derivable facts. The sums of random variables. Kind of what happens to the expectation and variance of sums. The reason why we talk about sums is because they help us talk about the arithmetic mean, which is kind of the simplest statistic. We had some facts about arithmetic mean. We had a fact about sample variance. Talked about how these things are kind of unbiased, what unbiased means. And then we talked about MGFs of sums, or MGFs of the mean. And that allowed us to derive the fact that if we have data that is normally distributed, the mean will also be normally distributed, which is it's a nice little fact. Not only do we know that the mean, the expected value of the mean is mu, and the variance of the mean is sigma squared, but in fact, if the data is normal, the mean is also normal. So we can stop there for today.